Hello, in today's video I'm going to show you how to solve a Cauchy-Euler equation, but one that has a repeated root. So it's a second order linear differential equation, but one that does not have constant coefficients. So in this particular example we have x squared um, d squared y by dx squared minus x dy by dx plus y equals 0. Now this equation, it turns out it has a repeated root when you start to solve it, which leads to one of the linearly independent solutions, but you can't have two identical linearly independent solutions forming the whole general solution. Um, Generally, they have to be different. So what we're going to do is we're going to use a substitution to find an indicial root of this equation, um, and then find the first solution, which hopefully should be quite simple. And then we're going to go from there and use a kind of an integral expression that will allow us to find very easily the second solution, the second linearly independent solution. And then from there we can get we can add the two together and find the general solution. So what we're going to try in this case is we're going to try a solution y equals x to the power m, and I hope you can see that there. Now this means that the derivative y dash is equal to mx to the m minus 1. That's the first derivative. The second derivative is y double dash equal to m minus 1 x to the m minus 2. That's just standard sort of high school mathematics for differentiating a function x to the power m. And there we've differentiated it once and then twice. Now what we do is we substitute this part of the expression in for d squared y by dx squared. We substitute mx to the power m minus 1 in for dy by dx. So just these components here, and we substitute the y equals x to the power m in there. Now, when we do that, we get x squared times this second derivative, which is m minus 1 x to the m minus 2, and here we've got a minus x times, well in this case it's just that first derivative, so we've got mx to the m minus 1 close bracket. We'll just get rid of that little bit of a comma there. And then finally we've just got y here, which is x to the power m, and that is equal to 0, right? Okay, well, this might look a bit complicated, but believe you me, we can simplify it and reduce this to a simple quadratic equation. So if we multiply, instead of multiplying the x squared by the x to the m minus 2 in the bracket, I'm going to take this x to the m minus 2 outside the bracket and multiply it by the x squared. So we have this, And in the bracket, we've got m minus 1, close bracket. And then here, we've got minus x times x to the m minus 1 times just m. And here we've just got plus x to the m equals 0. And by the way, this is a procedure that you would adopt in solving any Cauchy-Euler equation. There is another method using exponentials, but I think that's more complicated. It's a very good way of finding out the solutions, but I think this is better. It's simpler because it's easier to deal with. Y equals x to the m, because you just differentiate it straight away instead of messing around with chain rules using an exponential function. So anyway, you will notice, let's get a red pen here, this x squared x to the n minus 2 term is simply x to the m, right? And that's multiplied by m minus 1, close brackets, minus, well again here, let's use my red pen again, this is equal to x to the m times, in brackets, m plus x to the m equals 0, right? Let's just make that equal sign look a little bit clearer. Right. Okay, so what we've done here, I'll just write this as an aside in green on the board. Basically, taking this example here, x squared times x to the m minus 2 is the same as writing x squared times x to the m times x to the minus 2, or x squared times x to the m over x squared, and the x squareds cancel, leaving you with x to the power m. Exactly the same here. So we've got x times x to the m minus 1, or if you like, x times x to the m over x, which leaves you with x to the m. In fact, we'll just write that underneath because I want to leave a little bit of space. So, what you will notice is that we've got an equation which has factors in every part of it of x to the m. This means that we can take the x to the m out so that we have m minus 1 minus m plus 1, and that is equal to 0, right? Let me just shorten these brackets, make a little bit more room. So we've got that. Now x to the m, in actual fact, we should really have an a in there because this is valid for any solution of that form. So we really should have an a in. And I do apologise for making that error from the beginning. But all that happens is that we have an a. Let's just put the a in there. Right. A, 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 and of course we've got ax to the m multiplied by all of this equal to 0. Now this ax to the m cannot be equal to 0, which means that this part here, the quadratic, becomes m squared minus m plus 1 equals 0. We can simplify that And we can write m squared minus 2m plus 1 equals 0. So what are the roots of that quadratic equation? Well, we can solve this really easily by factorising it. And what we find is that we've got m there in each of those positions. Now, we've got to find something whose product equals 1 and whose sum equals minus 2. And that turns out to be minus 1, minus 1. Minus 1 times minus 1 is plus 1, and minus 1 times minus 1 is minus 2. So we have m equals minus 1, which is a repeated root. There we are. Okay, so I'm going to write the first linearly independent solution here, and I just move the camera down a little bit so that you can see what I have done there. So there we've got the quadratic equation, which we've simplified, factorised, and found that m is equal to minus 1 and minus 1, a repeated root. So what we'll do is we'll write the first linearly independent solution down here. I'll see if I've got a blue pen for that, and I probably can't find one. There is one about somewhere. Here we are. So the first linearly independent solution is y equals x. Well, let me just rewrite that again because I'm making a mistake. We've got y equals a times x. Well, we know that we've assumed a solution of y equals ax to the power m, but we've just found that m is equal to plus 1, right? n minus 1 equal to 0 yields a root of m equal to plus 1. So we'll just get rid of that plus sign because it's just equal to 1. M is equal to 1, so we've got y equals ax to the 1, or just ax. Sorry about all my mistakes. I do this. Right, so can you see that properly? Well, I hope so. That is one linearly independent solution. And I'm not sure that it's actually showing up very well on the video, so we'll just go over it in red. Is that a little bit easier to see? Y equals ax. Right, that's one linearly independent solution. Now, I'm going to have to clear the board to do the rest of the analysis. Okay, we'll just leave that bit on the bottom. There we are. Okay, let's move the camera up a little bit. Right, there we are. So, how do we find the second linearly independent solution? Well, there is quite a quick way of working this out, and we use the formula y2 equal to y1 times the integral of e to the minus p, or the integral of so it's the y1 times the integral of e to the minus integral of p dx over y1 squared dx. Now this looks complicated, but it really isn't. The only problem is that we need to know what p is. So what is p? Well, what we do is we take the original equation, the original Cauchy-Euler equation, which you will remember was x squared d squared y by dx squared minus x dy by dx plus y equals 0. Now, what we can do with this, to find p, we divide by x squared. We divide the whole of the left hand side by x squared, so that we get d squared y by dx squared minus 1 over x dy by dx plus 1 over x squared y. Now at this stage it doesn't really matter what this is, because this works anyway for a Cauchy-Euler equation. In actual fact, I'll just outline what 1 over x squared actually is. This is equal to q. In the analysis that you do for these types of equations, when you go back into the theory, this turns out to be q. Likewise, this is equal to p. The whole of minus 1 over x is equal to p, right? So what we can do is we can substitute this value, well, this variable, minus 1 over x, into this equation, and we know what y1 is. So we'll just write it down. Let me just clean the board again, and I've misplaced, there we are. Right, okay. Now, we know that y1 is equal to a times x, and we know that p is equal to minus 1 over x. So, get my black pen again. What we've got here is y2 equals a times x times the integral of e to the, well, a minus the integral of minus 1 over x dx over ax all squared dx. Now we can simplify this expression before we do anything else to it. Right, so we've got y2 equal to ax, and let me get closer to the board for this, times e to the integral of 1 over x dx over a squared x squared dx. Okie doke. Let's just draw a line down here so that we don't get the two sides of the board confused. We can take the a squared out here. In fact, we can just cancel the a in the numerator with the a squared in the denominator. So we get y squared equals x over a times the integral of e to the log of x. If you integrate e to the, well, if you have e to the integral of 1 over x dx, the integral of 1 over x dx is just log x, and that is divided by x squared, and then we have to do another integral, so stand by. What is e to the log of x? Well, the e, the exponential of a logarithm of a number is just that number. So it's y2 equals x over a times x over x squared dx. And if we simplify that further, we get y2 equals x over a times the integral of 1 over x dx. Now, let me just erase the rest of this. I'll check that everything on the board is showing up. Just about. So, we've got y2 equal to x over a times the integral of 1 over x. Well, we know that's the log of x, right? And actually, there's a constant as well. We put a constant in here. So we'll call this constant, what shall I call it? Well, I'll call it C, we'll call it C2. Or maybe we should just call it C1. It doesn't really matter what you call it. I just want to get everything consistent in the end. Now, if we multiply it out, we've got y2 equals x log x, and that's divided by a. X over a times log of x plus c1 x over a. Right, we are nearly home and dry now. So if I just erase this part of the board, how do we find our general solution? Well, we know that our general solution is y equals y1 plus y2. Okay? So, we've got y equals ax to the power 1. Do you remember, this is where I originally guessed that the solution y was equal to x to the power m, and I forgot to put the a in, and then I put it in afterwards. Well, when you're solving the Cauchy-Euler equation, you make that assumption, and usually you should put the constants in. But they're all solutions anyway. We know what y2 is because we just worked it out here. I'm going to write this bit first. So we've got c1 over a plus x over a. Oh, just a moment, I've missed out an x. You have to watch me because I do make mistakes being dyslexic. Plus x over a log x. We'll put that in brackets. So, okay, we have to just simplify this a little bit. So we've got y equals, well, a times x plus c1 over a times x is just, if you factorise it, it's just that, times x plus x over a log x, right? And of course we can just call these constants anything we like. So in actual fact our general solution is y equals, we'll call it alpha times x plus beta times x log x. And I'll write down what the constants are. So alpha equals a plus c1 over a, and beta is equal to 1 over a. Right, so that basically concludes how to find the solution of a Cauchy-Euler equation whose, like you could call it, an associated quadratic equation has a repeated root, meaning that it would appear that there are two repeated solutions, but you can't have that. So you take the first repeated root, substitute it into the general assumed solution ax to the m. So you substitute one of those repeated roots back into that. That gives you the first linearly independent solution. You then substitute that into that expression, or this rather, and you will find that you get a final solution, y2, out of that, and you just add that to that to find the overall general solution. So I hope that's helped and not been too garbled or messed up through making mistakes. As I said, I do these things, which is obviously, can be a bit problematic sometimes. But hopefully you've understood that and that it's been of help to you. So until next time, I shall say goodbye for now and see you later.